and wrap up our tour of these wide area networking technologies by taking a look at some more. We've been talking about dial-up, we've been talking about ISDN, we've been talking about frame relay. How about SONET? Yeah, SONET is circuit-based technology that delivers very high-speed service over our optical networks. SONET uses a nice fault-tolerant ring-type topology. So it's really cool. There's fault tolerance. There's the ability to be highly available. There's redundancy built right into the way in which SONET works. We typically have ATM or we have IP packet over SONET called POS. Those are the types of layer 2 technologies that we can run in addition to this layer 1 optical network topology. We have speed measurements for SONET thanks to what are called optical carrier rates. So we see an OC designation. I wanted to give you a couple of examples here to show you the variety of speeds that would be available. An OC1 would be a nice, solid 51 megabits per second, where an OC255 would be indeed a whopping 13.21 gigabits per second. So a lot of options when it comes to rates, when it comes to SONET SDH technologies. Another exciting technology in the area of wide area networkings is MPLS, the multi-protocol label switching approach. What MPLS really does is it goes in and it leverages the intelligence of the IP routing infrastructure, and then it leverages the efficiency of that Cisco express forwarding that we talked about. What it's going to do is it's going to take like any type of packet that you can imagine, and it's going to append a label to the packet. And then it's going to do forwarding very, very quickly through the infrastructure based on this label value. So the labeling of the packets is going to make for very efficient forwarding, and it's going to enable us to have MPLS work with a lot of different underlying technologies. So MPLS can be used in many different WAN physical and data link layer implementations because it's just slapping a label on the particular packet that's being forwarded over the wide area network. We know that traditional routing adds overhead, and the beauty of the MPLS situation is that this is only done a single time as you come into the service provider's MPLS cloud. And then once you get into the MPLS cloud, you can do forwarding of the packet utilizing the source address, QoS, maybe the destination address, so that it follows traditional routing. But if it's following traditional routing, it's able to be done at much, much higher speeds than with traditional routing. So MPLS, even if we're basing the forwarding based on the destination network, just like we do in layer 3 forwarding, we still can smash the speed records that traditional layer 3 forwarding can do. We have MPLS capabilities in our networks today thanks to LSRs, what are called label switch routers. We have edge LSRs called provider edge devices. These are the relatively busy devices. They are taking care of label distribution. They're forwarding packets based on labels. They're also putting the label on or taking the label off of the packets. We contrast these to simple label switch routers, not edge label switch routers. We would call these typically provider routers. And all they have to do is forward labels and forward packets based on labels. They are extremely efficient, beautifully efficient devices. Another concept with MPLS that I want you to be aware of is the fact that with MPLS, we have a separation of what's called the control plane from what's called the data plane. This really, really leads to a great efficiency in how these label switch routers work. There's resources that are constructed for the efficiency of control plane operations like the routing protocol, the routing table, the exchange of labels. And this is all separate from resources that are designed just to forward traffic in the data plane as quickly as possible. Remember how we said in Cisco Express Forwarding we would have what's called a forwarding information base? That's a copy of the routing table information in cache memory for quick forwarding. Well, sure enough, in the MPLS world, we have the label forwarding information base, which is for the blazingly quick exchange of traffic based on the label. By the way, the label itself in an MPLS world, it's a 4-byte label in length. Okay, so 4 bytes are added to the packet for MPLS. And how we forward all of the packets that are based on the same label, this is called a FEC, or Forwarding Equivalence Class. So let's say you want to take some traffic in the service provider's cloud and you want to forward it all based on some quality of service setting. Well, all of this traffic that is forwarded in this manner is part of the same FEC, or Forwarding Equivalence Class. Now, if you were to take this 4-byte MPLS label and you were put it under a microscope, you'd see inside that label that there is a 20-bit actual label itself. So there is a 20-bit label in the overall MPLS label, and that is the true label. And then there is a 3-bit experimental field, which is typically used for quality of service. In fact, it is so often used for quality of service that they have recently renamed these experimental bits to simply the traffic class field. Okay, so it is so often used for QoS that it's now been renamed simply traffic class. There's the bottom of stack bit, which is used to indicate you've gotten the bottom of the labels. And then there's an 8-bit time to live field, because we certainly don't want looping in an MPLS world. We don't want traffic to loop, and a time to live field assists us with loop prevention. So the label consists of the label itself, a quality of service marking field, a bottom of stack bit for when we have to stack labels on top of each other, and a time to live field to guard against loops. Why might we have a stack of labels? Why do we have to have this bottom of stack bit to say we're at the bottom of a stack of labels? Well, we often run into these with MPLS VPNs. MPLS VPNs are so cool. As a matter of fact, the MPLS Layer 3 VPN, it is the #1 reason we have MPLS implemented today. The most popular application of MPLS, why it is so prevalent today, is for these Layer 3 MPLS VPNs. Here's what they look like. You've got a service provider that is offering the MPLS VPN services. And what it's able to do is it's able to take these provider edge routers and it's able to connect them to different customers. Customer A, customer B, customer C. And then maybe it's got a provider edge router over here, we'll say PE2, and it connects out to another customer A location. There is a customer D out here. There's another one of the customer, let's say, B locations. And with the multi-layer MPLS approach here on these devices, what happens is customer A between these two locations just gets totally transparent, seamless communication capabilities thanks to MPLS. And by the way, the customer doesn't run anything by way of MPLS. I mean, the customer A is just maybe running, let's say OSPF here and here. So the customer is just running our standard OSPF. It's not doing any fancy MPLS whatsoever, but the multi-layer, multi-protocol label switching MPLS VPN service provider is using MPLS technologies in order to carry the traffic between these PE devices through its cloud. Now, when we have one of these MPLS VPNs, we end up with a stack of labels because a label is used to identify customer A, and then another label is used to take the forwarding through the cloud. So label stacks are very, very common. They're used in these layer 3 MPLS VPNs. So the layer 3 MPLS VPN that we see here, very, very powerful, flexible option for service providers to just give customers the transparent WAN access connectivity they need. And it's all done very easily and simplistically thanks to MPLS for the service provider. This is hugely scalable for the service provider. Very, very easy for them to add customers, add sites, and add more customers, and add more sites. It's all a very, very efficient infrastructure for them to provide these VPN services. There is indeed different flavors of MPLS. There is the very, very popular frame mode MPLS, and this is where the label is placed between the layer 2 and layer 3 header. As a matter of fact, we call this layer 2.5. You'll often see this termed as layer 2.5 because the MPLS label is being shimmed between the layer 2 and layer 3 headers. This is the most wildly popular MPLS flavor. It's called frame mode. But to give you the complete story, I wanted to mention cell mode MPLS. And you know what uses a cell switching technology? We mentioned it a bunch of times. Sure, it's ATM. So in cell mode MPLS used by ATM, there are fields in the ATM header, and those fields are used as the label. So 2 different flavors of MPLS. And it basically depends on whether or not we're using ATM. In MPLS, one of the big issues that we have to solve is who's going to take care of inserting and pulling off the labels. In creation of labels, we have the ingress edge LSR. And then for popping, it's called popping off the labels, we have our egress edge label switch router. Notice the label switch routers in the interior of the MPLS topology. Notice they got it made. All they're doing is what's called label swapping in order to forward traffic along in a particular path. So very, very efficient, our ability to forward traffic based on labels. Obviously, the devices need some kind of way in which to exchange the labels that they'll utilize for forwarding decisions. The way in which the devices distribute the labels is thanks to a protocol. The most popular approach is the label distribution protocol. It's a session-based UDP technology that allows for the exchange of labels. UDP and multicast are used initially to set up the peerings, and then transmission control protocol makes sure there is a reliable transmission of this important label information. One of the coolest names in all of Cisco networking is penultimate hop popping. Penultimate hop popping. This is classic. What happens with penultimate hop popping is the second label switch router towards the exit. That's what penultimate means. It means second to last. The second to last label switch router in the MPLS path, it will be the one that pops off the label. This adds efficiency to the overall operations of MPLS. Discussing MPLS to this level may be going a bit farther than you need for CCDA, but I just wanted to sound really fancy and say the words penultimate hop popping in this class. Some more terminology that you have with MPLS is you have this concept of a route distinguisher. This is a neat concept. This is how the service provider can tell the traffic of different customers. This allows different customers that are participating in the MPLS VPN to use the exact same IP address space. Ah, cool. So you can have customer A using RFC 1918 private space of 10, 10, 10, and you can have customer B using the exact same 10, 10, 10 subnet. The traffic is able to be distinguished from each other utilizing a route descriptor. Something else that's really cool is devices now can create their own virtual routing tables called VPN routing and forwarding tables. So a provider edge router can take all of the customer A data and store it in its own virtual routing table. And then it can take all of the customer B information and store it in a unique virtual routing and forwarding table for that particular customer. How do we carry traffic? How do we carry prefixes through the VPN multi-protocol label switch cloud? Well, we rely on what's called multi-protocol BGP in order to carry these special VPN v4 prefixes. We can filter customers being able to access each other's prefixes with what we call import and export targets. Certainly, one of the most growing and popular WAN technologies is MPLS. So I wanted to give you a nice exposure here to how MPLS functions and key terminology that we would have in an MPLS environment. Another technology that we'll find out there for wide area networks is called DSL, digital subscriber lines. This is a way in which to provide higher speeds than ever before achieved over those traditional copper PSTN lines. How did they do DSL? How in the world did they do it? Well, they went ahead and took advantage of frequencies that were available in those copper voice lines that weren't utilized in the voice calls. One of the things that you'll often see with DSL is you'll often see to it generically referred to as XDSL. Why do they say XDSL? Well, because there is an overwhelming number of variants of DSL. There's asymmetric DSL, there's symmetric DSL, there's high data rate DSL, there's very high rated data rate, there's rate adaptive DSL. I mean, it's just amazing. There's even an IDSL, and the IDSL is based on none other than, sure, ISDN technologies. So there's just a wide variety of DSL variants out there that we tend to just generically call XDSL. By far the most popular form of DSL, and that's because it is the residential DSL that was very popular for a while, is ADSL. It's called asymmetric DSL. Why is it called asymmetric? Well, because with ADSL, like so many broadband technologies, your rate of downloading will be different from your rate of uploading. We typically have a higher download speed and a lower upload speed. And that's exactly how ADSL works. You get fast downloads, relatively slower uploads, and this is why it's called asymmetric. By the way, with asymmetric DSL, here's another great piece of terminology for you. You end up connecting to what's called a DSLAM at the service provider. DSLAM stands for Digital Subscriber Line Access Multiplexer, a way to get a bunch of different individuals onto the ADSL network. One of the issues with ADSL is you can only be so far away from one of these DSLAMs. So there are distance limitations with subscribers as far as how far away they might be from one of these DSLAMs that makes all the magic of DSL happen. Another broadband WAN technology that we see in use today is cable. This is so cool. With cable technology, we're taking that existing coaxial that was previously used just for bringing cable television signals, and we are figuring out how to squeeze more bandwidth out of the coaxial and bring high-speed data networking to that coaxial cable. This is brought to you thanks to the use of a cable modem on the customer side, and then on the service provider side, we have what's called a cable modem termination system, or CMTS. Your modem technology utilizes what is called DOCSIS, which is Data Over Cable Service Interface Specifications. So your local cable modem is going to use the DOCSIS standard to make sure it functions properly over this wide area networking technology. Another technology can be used in conjunction with cable, and that's PPP over Ethernet. This is pretty cool, and this can be used between the cable modem and your devices in order to add security to the cable modem infrastructure. So in other words, you can log on and you can provide a username and password that has to be authenticated in order for you to use the cable service. How is the username and password carried from your Ethernet connection to the cable modem and beyond? It's done thanks to the point-to-point protocol running over Ethernet. Yet another option for carrying data across wide areas is the area of wireless. There's mobile wireless and a lot of different flavors of mobile wireless, like our 3G wireless networks that we love on our mobile phones these days. And then there's wireless local area networking, like 802.11b and 802.11n and 802.11a. We'll be studying wireless local area networks in the CCDA course. As a matter of fact, it's our last chapter. So on day 5, to wrap up the 5-day boot camp, we'll be studying intensely these wireless local area networks. You'll often hear about bridged wireless wide area networking, and this is like when you want to do line of sight connectivity, maybe between 2 buildings in your campus. We have these antennas that point at each other and go ahead and send wireless signals back and forth between the buildings as a way to connect and bridge the local area networks that make up these buildings together. Yet another WAN concept that we want you to be responsible for is the knowledge of what's called dark fiber. You see, early on when times were good and the internet bubble hadn't burst yet, all of these companies were installing a dramatic amount of potential bandwidth through fiber optic cable installations. Since most of the expense went into the labor of putting all this stuff in, and relatively little expense went into the fiber itself, there was tons and tons of bandwidth that was laid. It's now, in many instances, completely unused, so that's why it's called dark fiber. Service providers will come along and they will go ahead and take this unused fiber in order to build what are called our SONET networks. We discussed SONET earlier. Or they'll do what are called dense wavelength division multiplexing networks. More on DWDM in a moment. So this will allow end user enterprises to go ahead and expand their Ethernet implementations into local area networks. This is where we get into a concept called Metro Ethernet. Wow, we're able to take advantage of this dark fiber and we're able to connect what we would have never been able to connect via Ethernet before, Ethernet connections over these larger distances. This is where we can get into metropolitan area networks, or MANs. By the way, dense wavelength division multiplexing allows the use of different wavelengths of light over one of these optical fiber strands in order to once again add new bandwidth and add new services to existing channels of fiber. Wow, how amazing. So just like earlier when we talked about a coaxial cable, how we could use different frequencies within the coaxial cable, now we're talking about using different frequencies within the optical fiber strand. A technology that grew out of this concept was Cisco's long-reach Ethernet. Notice Cisco has given up on this initiative and no longer produces long-reach Ethernet switches, but you are responsible for knowledge of this technology as a CCDA. Long-reach Ethernet supported 5 to 15 megabit per second performance options over typical telephony category wiring of distance of up to 1.5 kilometers. Long-reach Ethernet is a MAN, or Metropolitan Area Network technology, that's very, very similar to VDSL. So this grew out of VDSL technologies. And by the way, sometimes you'll refer to this long-reach Ethernet as Ethernet in the first mile, or EFM. That was another term that was used for long-reach Ethernet. Get ready in the CCDA certification exam to be able to answer questions that bring a lot of these technologies together for you, like which option for WANs below would provide a low initial cost, medium bandwidth option for a teleworker connection to the enterprise edge? Would it be MPLS, ISDN, cable, long-reach Ethernet, or SONET? Yeah, a low initial cost, medium bandwidth option for a teleworker, that's cable, isn't it? Yeah, that's cable. It's common sense. Long-reach Ethernet, nah, too high a bandwidth. ISDN, too low a bandwidth. MPLS and SONET, massive bandwidth capabilities, but at a real high cost. So the low-cost, medium bandwidth alternative that would be perfect for a teleworker would be cable. So get ready to answer questions of this nature when it comes to these many, many different wide area networking technologies. Well, next up in our CCDA event, we'll start looking at some of the design methodologies and design considerations that you want to evaluate carefully before you devise and you design the Enterprise Edge module. So we'll be back in the next lesson to discuss key criteria for your proper design of this important module of the enterprise architecture.